So let's so I talked about the support vector machines. Now remember with the housing, we said you can combine the data to make new data fields by combining the existing ones. And here's something your scientists probably know. If I have data, I'm trying to separate the red from the blue, or red from the green here. Well, this line would work and that line would work. Any decision line would work. All the reds are on one side and all the greens are on the other. So where's the best line to choose? Support vector machines do this. They choose the line that has the biggest road, the biggest margin. That would seem like the thing to do. You use the angle and the width of this so you have the biggest separation between them. That is the best line to use to separate these two categories. This has a very strange consequence. That line is determined only by these dots on the edge. The other dots don't matter at all. If you remove these dots or move them to a different location, it wouldn't change the location of that line at all. So you can calculate this thing this is called the support vector machine, and the dots on the edge are called the support vectors. So this sounds so stupid you would think it would be useless, but it's not useless at all because as you know from science, if you have something that is not a straight line, you can make it a straight line by putting it on log paper or by plotting against x squared or x cubed or something like that. If you plot on some funny kind of paper, almost everything becomes a straight line. And so this turns out to be much more useful than you might think and very easy to calculate. And of course, you can relax it so you allow some margin and error, and then you use more dots than the ones right on the edge, and you can deal with data that actually overlaps by blurring it a little bit. So let's try making support vector machines, and these are going to come back later. These are really useful. So I'm going to make a new notebook. I wonder if I move to trash. That's probably what I should be doing. And then make a new one here. That might be a little more efficient. All right. So this will make a fake bunch of dots that are just Gaussian split so we can practice separating them apart. It's going to make red and blue dots. Okay. Downloading some libraries. This is the SecML library, a machine learning specifically for security, which we're going to use a lot of because it has attacks in it. But for now, we're just going to make red and blue dots, and then we're going to create and train a support vector machine to separate those dots and plot the results with the decision boundary. And you'll see that here. This is the classifier SVM, a trained model to make these support vector machines. There's my dots, and they don't overlap, so you can draw a line that will 100% separate those dots. And the support vector machine will figure out the best line to separate those dots, and there it is. Okay, now this is the line that most efficiently separates the red from the blue. Notice here the vertical scale goes 0, 1, 2, and this scale goes 0, 1, 2. Now, suppose you expand the Y scale. And remember, we had that housing data where you had things like latitude and longitude and dollar amount and count of houses. You had all these numbers that were not remotely on the same scale or in the same units. So this is very common that your original data doesn't come with the same scale. So I'm going to just expand the vertical scale. So this is going to go up by hundreds where this goes up by ones, which is the way real data typically is. You've measured things in different units. Now, if you create and train the model, you're going to get a very different result. You get a very different. Now, the reason this happens is because when you made this scale hundreds, what the model does is calculate the mean squared error. And you told it vertical errors count 100 times more than horizontal errors. So it has to choose this line instead of the other. This is why you have to scale your data all the time. The number matters, even though this might be counting people and this might be counting dollars. So it really makes no sense to compare those numbers, but the model doesn't know that. It just uses the numbers and calculates the mean squared error. So the human has to apply the intelligence to normalize the data so the number actually reflects the importance of that measure, which is a human judgment. It's not in the model. And so you can change the Y magnification. Now let's try support vector machines for a more realistic data set that can't be 100% separated. So we'll make a model with more standard deviation so that the dots actually overlap. Okay, now we have red and blue, and you can separate the red from the blue to some extent, but you clearly can't do it perfectly anymore. And there's a support vector machine version that allows you to have these fuzzy boundaries. All right. And so now what happens is, since you cannot have a perfect separation, you have to add a regularization parameter. And this is very common. You have a problem where there is not one unique solution, so you put in a smoothing parameter, which is this C parameter, and you just try various values of that. So instead of minimizing the error, you minimize the error plus a measure of the complexity of your model. It's like I don't want it to have extreme tilts, so I'll add some measure of the slope. Or I don't want it to be too curvy, so I'll put in some measure of the curve. That's what this C is. So instead of just using the data, you also have a smoothing parameter. And since you don't know what level of smoothing parameter to use, you just move it through a range. So here it'll go from 0001 to 001, move it up by various factors of 10. And so with a really small smoothing parameter, the smoothing parameter is too effective, and I've called all the dots blue. Well, that's no good. But here, it's getting a little better, but it's still terrible. This looks like 0.001. 0.01 is a pretty good fit. And you get pretty much the same thing at 0.1 and 1. So this is what you do. You add smoothing parameters that will make the model more believable and not just that follow the data, and you try various ranges to get an appropriate fit. So there's a whole lot more approximation and human judgment in this than you might imagine. When you say the machine just learned on its own, that's not really true at all. Humans guided it to a believable answer to a large extent. And now, what about if you have data sets that you can't fit with a line? Let's have curvy data. There's this thing called moons that creates curvy data, where the blue ones are up there and the green ones are down here. Now, if you try to make a linear support vector machine model here, then what you can do is add polynomial features. See, now what I do is instead of just trying to fit a straight line to separate these, which is pointless, you include more dimensions. Now, you don't just have x1, you calculate x1 squared and x1 cubed, and x2 squared and x2 cubed, so you have a six-dimensional space. And in that six-dimensional space, it's now a straight line. Like I'm saying, if you use funny enough graph paper, anything becomes a straight line. So any decision boundary that is like 10x cubed plus 3x squared plus x is still a straight line in this high-dimensional space. That's what we're doing here. So this will add polynomial classifiers to it. This is how it works. You have polynomial features, you go to a scalar and a linear. So a linear support vector machine can fit curves because you include data points that are created from the existing ones with the powers in it. And so now you can fit a boundary like that. That is a straight line in a high-order six-dimensional space, projected back down here, including the squares and the cubes of these parameters. And so you can do it again. And if you make a two-order polynomial, then it can't do it. It needs three polynomials. It needs cubic terms to trace out that complicated shape. And there's a thing called a polynomial kernel, which is a mathematical trick to do this with much less computation, covered in those textbooks. Just another way to do the same thing that turns out to save a lot of computing time really fast. So now we can get the decision boundary of the polynomial kernel. All right, and there it is again. Now, yep. And so you could also change the degree to a higher degree. If you go up to the 10th degree, then you can have even more complex curves here that really is still just a straight line. So that's what I wanted to show you, the joy of support vector machines and how you can do surprising things with nothing more than really a straight line. So let me stop this one.